it's easy to let that picture lead one to think that wave functions are describing physical objects out in the world. And, when I think students arrive in a quantum mechanics class for the first time, without having studied the theory, they may think that, okay, every particle's got some wave function. The wave functions are kind of like waves empty space is kind of like the ocean, and all the particles are kind of like small little waves moving around in the ocean. And that's actually not the picture that we get even from the textbook theory of quantum mechanics. In the textbook theory, a wave function is the assignment of a complex number to every possible configuration of your system. If you're talking about a single particle, nothing else, then every possible configuration is every possible location the particle can be in. Each location is labeled by 3 numbers. It's x, y, and z coordinates if you want. And so the wave function takes in those 3 coordinates and assigns it a complex number. And then we're supposed to do a mathematical operation with that complex number, and out comes a probability. More precisely, a probability density, but a probability per unit volume that a measurement will find the particle at that spot. So the wave function can be thought of as the assignment of a special complex number to every point in 3-dimensional physical space, where you do this operation. It's called mod squaring. You do this operation, and then it tells you the probability, roughly speaking, with which a measurement will find the particle at that location. So it's very easy to think that a wave function is like a field, like the electric field in 3-dimensional space. But if you have 2 particles instead of 1, then the possibility space is much more complicated. We call this possibility space configuration space, because each possible configuration of a 2-particle system requires 6 numbers, not 3. You need to know x, y, and z for the first particle, and you need to know x, y, and z for the second particle. So the wave function assigns a complex number to a point in a 6-dimensional space. 6 dimensions because you need 6 numbers to specify its points. And that means a 2-particle wave function is a function, we say, whose domain is a 6-dimensional space. 6-dimensional space is not physical 3-dimensional space. If you've got 3 particles, it's a 9-dimensional space. If you've got 10 particles, it's a 30-dimensional space. And actually, our universe does not have a well-defined number of particles at all. Our leading physical model for the universe, at least for the non-gravitational parts of the universe, is the Standard Model, which is based on a set of models known as quantum field theories. And in quantum field theories, particles are emergent excitations of these sort of delocalized entities called quantum fields. And the number of particles can change from moment to moment. It's not always well-defined. So it's not even clear how to even think about wave functions that live in anything like physical space in the universe as we know it. So I don't mean to say that we're teaching our students wrong. We're not. I mean, students will learn this as they go on in their physics trajectories. But I think a lot of people on the outside, or new students who haven't yet started their own journey in physics, have a certain idea about what wave functions are like that's actually quite different from the way we use them in practice. I don't know if that clarifies what you were asking about.
Okay, so you have a lecture about how Hilbert spaces are also not real. I'd like you to talk about that. Now, it's my understanding that you more precisely said Hilbert spaces are redundant in the same way that gauge symmetries are redundant, or the gauge transformations are redundant.
So at this point, if it's all right, let me do a little bit of history, if it's okay. So where does quantum theory begin? Lightning, grand tour of quantum theory. There are these actual physical objects called black bodies. They are chambers that are heated, and a little hole is poked in them. I mean, you don't really poke a hole in them. It's more complicated. But this is I'm very much a theorist, and my picture of experimental physics it should be better. And I apologize in advance to anyone who's an experimentalist listening to me. But these were actual systems. People actually built these things. They were these chambers. They would heat them up, and then they would have a little hole in the chamber through which they could see radiation coming out of them, and they could put that radiation through experimental devices that could show them how intense the radiation was as a function of wavelength. Right? We all know that different wavelengths of light correspond to different colors in the visible range. And if you go outside the visible range, you have very long wavelengths that are infrared, or microwave radiation or radio waves. And at the very short wavelengths, you've got X-rays and so forth, gamma rays going all the way out, ultraviolet X-rays, gamma rays going all the way out to very short wavelengths. And you could just ask yourself, if I plot how strong the radiation is as a function of wavelength, what kind of pattern would I expect to see? And the pattern that was revealed in experiments was difficult to explain on first principles theoretical grounds. A very important physicist, Max Planck, in 1900, found a way to generate a theoretical prediction of what this black body radiation curve should look like, and it agreed with experiment. But in order to get there, he had to kind of hack his formulas. He had to introduce a fudge factor. He had to assume that radiation in this chamber could only occur in quantized amounts. That is, there were different wavelengths you could produce, but each wavelength could only be excited in discrete steps. This led to the quantum hypothesis. This was his quantum hypothesis. And there was a sort of parameter that told you how big you wanted to make these steps. Today we would call it a regulator. And this parameter, we now call it h, little h. We call it Planck's constant. Planck introduced it. And then I think at one point his idea was he wanted to introduce an intermediate step in the calculation. And once he'd calculated everything, send this clearly, in his mind, unphysical parameter to zero. But whenever he tried to send it to zero, he would get the wrong results. He realized this parameter was not zero. It was very small. It was, today, it has a value, that's of order 10 to the negative 34, 10 to the negative 33 in conventional units. And he couldn't get rid of it. And so people had to accept that there was this basic discreteness in nature he couldn't explain. And then for the next 22, 23 years, the period from 1900 to 1922, 1923, physicists working on these questions were living in a time that today we call the old quantum theory, a paradigm we call the old quantum theory. The old quantum theory was based on a mixture of physical pictures of particles moving around in space, in orbits, like in atoms, and then a collection of ad hoc formulas and rules that people didn't fully understand that seemed to capture some of the observations that were coming out of experiment. But it was a very murky time. There wasn't anything like an underlying theory from which this whole picture emerged. And the formulas weren't perfect. They didn't work exactly right. In 1913, Niels Bohr proposed his famous model of the hydrogen atom. This is a model in which you've got the nucleus, and for the hydrogen atom, it's just a proton, positively charged proton in the middle, and an electron going around. And by making use of these sort of heuristic formulas that were characteristic of the time, Bohr argued that the electron could only be in certain definite orbits, and when it transitioned between them, its energy changed in discrete steps, and whenever its energy changed, it would either absorb or emit radiation in discrete amounts. And with this, he was able to account for the particular colors of radiation that we would see emitted from excited hydrogen atoms or that were absorbed by hydrogen atoms, the so-called line spectra. And we also found that other atoms had line spectra as well. Famously, helium was discovered because we looked at the spectral lines from the sun, and after accounting for all the spectral lines we knew about, there were still some more that we didn't account for. And so people conjectured there was a new element. They called it helium, from Helios, the sun, and eventually we found helium on Earth, but it was first discovered on the sun. So this was obviously a very important thing, and Bohr ended up winning the Nobel Prize in 1922 for this Bohr model. But by around 1922, certainly at least by then, people were becoming very skeptical, because people couldn't take these clear pictures of particles moving in definite ways, particles interacting with fields like the electric magnetic field, which were well understood by this point. They couldn't take this world picture, this ontology, this picture of what was physically out there. They couldn't find laws that, when combined with this picture, gave you the right predictions, that gave you an empirically adequate, empirical meaning, subject to experiment, empirically adequate, a theory that was able to account for the things we were seeing and make predictions that were regularly confirmed.
Don't forget to follow Theories of Everything with Kurt Jaimungal on Spotify for exclusive content and in-depth discussions. Your support on Spotify helps us grow and to reach more curious minds like yours. Check out the link in the description and join the Core Toe community on Spotify today. See you there.